Okay, so good morning, everyone. It's a pleasure to have André here today with us. So André did his studies in the Federal University of Espírito Santo. Now he's a professor in Pernambuco, and he works with conformal field theories and orbifolds and applications to holography, for instance. And today we will be talking about special system D1, D5, hopefully. And yeah, let's give him his chance to speak. Okay, thanks, André. The stage is yours.
Hi, hello, good morning. Thank you very much. Thank you very much for the invitation. It's a pleasure to be here in Natal. I had never been here before. And well, I'm going to talk about something that is related to my research. What I actually work with is mathematical physics, and it's very technical and not very interesting for giving a talk. So I try to, this talk is about the context around it. I'll try to explain, give a general overview of an instance where conformal field theory can be used to describe quantum degrees of freedom of a gravitational system, which looks like a black hole. Well, this is a picture, this is a GIF of some stars at the center of the Milky Way. People took pictures of these stars for 20 years and reconstructed the orbits. And if you plot the orbits of these stars, they look like that. And they all revolve around a point in the middle, which doesn't appear here. It's black. It's dark. By the velocity of the orbits, you can compute using gravitation that here in the center must be a very massive object, which is black. And so this was a candidate for the black hole in the center of the galaxy of the Milky Way. And a few years ago, people actually took a picture of the same spot. This is the black hole in the center, where around which those stars orbit. It's a massive black hole. It has 4 million sun masses. It has a very large radius. This yellow thing is actually matter orbiting around it, and in the center there is the actual black hole. This picture here is one of the many recent confirmations that black holes are physical objects that exist and that behave much like general relativity tells us that they will behave at least outside the event horizon. You also have gravitational waves and such. And the combination of pictures with gravitational waves, the amount of evidence of the existence and behavior of black holes by now is very large. So black holes are the simplest objects in gravitation. They are almost perfect objects that we can describe by some reason. We can describe them analytically. In the theory of gravity. The theory of gravity is a theory of the geometry of space-time. Geometry is basically Pythagoras' theorem. In flat space, you have time as one of the hypotenuses of the triangle, and what gravity is what gravity makes is to change the Pythagoras theorem, curving the geometry and changing the paths of lights and of objects that move in this curved space. The way the space is curved is given by Einstein's equation. You put matter in space-time, and it has an energy and momentum, and it creates a geometry. So this is classical general relativity, and one of the simplest solutions of this theory is the Schwarzschild black hole, which is given by this large Pythagoras theorem. You have here a sphere, time, and a radius, and if you focus on the radial part with time, it has a structure like this. There is a factor here and a factor here in the two coefficients of the Pythagoras theorem, which are the same, but one is the inverse of the other. There is a -1 power. These factors, they are responsible for a specific kind of warping of space-time that changes the paths of light in such a way that there is a region, a sphere, where that factor vanishes, in which light cones tilt too much towards the interior. This is the radial coordinate. And so when you are inside here, your light cone is tipped so much that you can't escape anymore. You always have to be inside the light cone. And so when the wall of the light cone is tilted in this way, you can't escape. And your fate is to go and hit the singularity in the middle. This is an event horizon, what we call an event horizon. In general relativity, it's empty space. There is nothing here. If you throw something here, it quickly goes inside, and this region is empty. And it is the boundary of a black hole. It is the beginning of a black hole. That's the threshold inside of which light or matter can't escape. So in the 60s and 70s, Hawking proved, Hawking, Bekenstein, Penrose, these people studying classical general relativity, they saw that you have a relation between the energy that makes the black hole, the mass inside, and the area of this event horizon, this black sphere around it. You can also make it spin with an angular momentum J, and you can also put electric charge. If you ignore that, to be more simple, the relation between the energy, a small increment of energy of mass of the black hole, and a small increment of the area is given by this. If you throw matter inside, the black hole increases a bit. The area of the event horizon increases a bit, like this. And this coefficient here is the surface gravity of the event horizon. This is a completely geometrical equation, but Hawking and Penrose and Bekenstein started to make an analogy. If you call this energy and you call the area an entropy, this coefficient here should be a temperature. Why should you call the area an entropy? Because if you take a kettle of boiling water and go near the black hole, the boiling water has entropy. And if you leave it fall inside the black hole, the entropy disappears. And the only thing that happens to the black hole classically is that it increases this area. So if the second law of thermodynamics is not violated, this area must, the increase of this area must correspond to an increase of entropy of the black hole to compensate for the disappearance of your kettle that you threw inside. So the area of the black hole should be related to its entropy. And by analogy, this coefficient, this kappa, should be corresponding to the temperature. Later, Hawking made a precise computation with quantum fields in the curved spacetime and showed that the black hole actually evaporates by a quantum mechanical process called Hawking radiation. And it evaporates like a black body with this temperature given by the acceleration here. So the analogy between entropy and area is not anymore an analogy, is actually a way that entropy is stored inside the black hole. It's in its area, the area of its event horizon. The black hole in the center of the Milky Way, if you use the size of its event horizon to compute the entropy, you compute the area, you find an entropy of this order, which is a lot of, would correspond in quantum mechanics to a lot of microstates, the exponential of this, a number of microstates, which is the exponential of this number. It's a large number of internal degrees of freedom that give this entropy. However, the black hole itself, in classical general relativity, is a very simple object. It doesn't have any parameters. Actually, it has three. It has the area, the angular momentum, and the charge. And 3 is very different than the exponential of 10 to the 90. So where are the degrees of freedom that correspond to this large entropy of black holes? It must be related to a quantum description of the gravitation that creates this object. So it's a problem, an intrinsic problem of quantum gravity. There are many proposals of quantum gravity. String theory is perhaps the most well accomplished, and it gives an answer. One of the great successes of string theory as a theory of quantum gravity was to give an explanation, albeit in a simplified, controlled environment, to how it is possible to find those large number of states. And the answer is related to conformal symmetry. So I'm going to talk a bit about conformal symmetry first. What is conformal symmetry and conformal field theories? Conformal transformations are a generalization of the ordinary Lorentz transformations. So you have space with coordinates x, and you can measure distances ds squared. This is the Pythagoras theorem. And Lorentz Poincaré symmetry is a set of transformations that you can make to x that preserve the distance. Conformal symmetry is a generalization of that in a way that you don't need to preserve ds. You can multiply it by an overall factor, sometimes called a conformal factor. So the geometric picture here is that you can, when this omega is different than 1, you are changing the lengths of things, but the ratio of internal products is such that cancels this, so angles between lines do not change. So conformal transformations are a set of transformations that preserve angles, do not necessarily preserve length, and we can try to find what are the allowed transformations that do this. So first, you have transformations that preserve length. The omega is 1. And these are the usual transformations of space. You can either have translations, they don't change the s. And you can have rotations, they also don't change the s. These are Lorentz Poincaré symmetry, or Lorentz boost. You can make translations in space direction and rotations in space direction, or space-time directions, and you have Lorentz Poincaré symmetry. The new thing about conformal transformations is that you can change the length, and the simplest way to do that is by dilations. You take x and you multiply by a factor of lambda. If this factor is larger than 1, you are increasing the size of things. So you change lengths now, but in a way that the overall change is just a multiplicative factor in the hypotenuse. And you can also make a different transformation, a more complicated one, which is called special conformal transformation like that, which is related to inverting x to 1 over x and translations and a combination of this. This is what happens in dimensions. If space-time has dimensions 3, 4, 5, any number except 2. In 2 dimensions, something different, something special happens. So the important thing is you have scale transformations, simple scale transformations. You just dilate space, or you can do a more complicated thing, which is that special conformal transformations. But in 2 dimensions, it turns out that if you parameterize this plane, the original plane, by z, the complex number, any map which is holomorphic, that is, only depends on z, works. Any transformation with any f that you put here will only change the metric by an overall multiplicative factor and will preserve angles. This is a well-known fact from complex analysis. So you can simply choose any holomorphic function, and it will deform the space in any way, but in such a way that for the grid is very much changed, but the angles here are always 90 degrees because they were initially 90 degrees. There is an infinite number of holomorphic functions. You can make them up as any way you want. So you actually have an infinite number of symmetries in 2 dimensions. Since small and large sizes are equivalent, you kind of lose the notion of distance. And conformal field theory is useful to describe systems which do not have an intrinsic length scale. For example, in condensed matter and statistical mechanics, condensed matter, no, I don't know if that's, I mean, in statistical mechanics, when you have a system in a second order phase transition where the correlation length blows up and you have correlation in all lengths, this is can be described by a conformal theory, in many cases a conformal field theory. So that's it. You have relevant effects at every length. You lose the notion of length. You only preserve angles. And in 2 dimensions, you have an infinite number of possible transformations you can do. So you have an infinite number of symmetries in 2 dimensions, of conformal symmetries. Nether taught us that when you have symmetry, you have also a conserved current. So these changes in symmetry, these infinite number of symmetries in 2 dimensions, what currents do they conserve? Symmetry of space-time, translation and in space and time, give us a thing called energy momentum tensor. Energy is the charge conserved by translation in time, and momentum by translation in space. And the combination of that is what we call the energy momentum tensor. In 2 dimensions, in a CFT, the non-trivial part of the energy momentum, or the stress tensor, is a holomorphic function. It is traceless. The tensor itself is traceless. And the non-trivial component is a holomorphic function. And you can expand an holomorphic function in a Lorentz series. And the coefficients of the Lorentz series will be your conserved charges. Since you can make up any function, the only thing is that it must be holomorphic. You have an infinite number of charges. These are the infinite symmetries of 2-dimensional CFT. These things, when you quantize the theory, these coefficients, they become operators, which make T an operator, and they satisfy a commutation algebra, like angular momentum, when you quantize, satisfies a commutation algebra, etc. The algebra that these Ln modes satisfy is called a Virasoro algebra, and it looks like this. It has an important property. Well, we have an infinite number of L, so an infinite number of commutation relations, and it kind of looks like an angular momentum algebra in this part. But this part here is special, the second term. It is multiplied, it has a number, C, this is a number, not an operator, which is called the central charge of the theory. Mathematicians call this a central extension of a Lie algebra. This part is called the Wheat algebra, and the quantum theory has this correction. Well, it's not a correction, it's a new term, which is called a central extension. This number that appears here characterizes the specific CFT that you are dealing with. The algebra itself appears in any CFT. You can have the CFT of bosons, the CFT of fermions, the CFT of more strange objects, I don't know, called ghosts. Or you can have many CFTs. Some describe the phase transition of the Ising model. Some describe polymers. Some describe string, the word sheet of a string. The difference between them at the level of this algebra of the symmetry, of conformal symmetry, is this number here. It changes from CFT to CFT, and it kind of counts the number of degrees of freedom of the CFT. If the CFT has a lot of degrees of freedom, this number adds up. Well, there is a formula proven by Cardi that states with energy n, for large n, they have multiplicity given by this, the exponential of the square root of the central charge. I put this here, kind of, we are going to forget about it because it's not going to appear until the very end, but it's going to appear later. So the multiplicity of states is given by the central charge. And let's keep that in mind. So what is ADS-CFT? ADS-CFT is one of the results coming from string theory that relates conformal field theories, which are field theories with conformal symmetry, to what I talked about, conformal symmetry. You enhance the Poincare symmetry by by allowing a few more transformations or infinite more transformations in 2 dimensions, but it's not gravity. It's made in flat space. So it's not a gravitational theory. It's a field theory without gravitation. ADS-CFT is a correspondence between gravity, classical gravity, in ADS space, and quantum field theories in spaces without gravity. And the correspondence is such that the dimensions are different. So if you have ADS in d dimensions, ADS is a space-time which is empty. It only has a negative cosmological constant, and so it has a lot of symmetries. Actually, it has the maximum possible number of symmetries in a given dimension. And it kind of looks like, the sphere is a space with a maximum number of symmetries, but it has positive curvature. A Pringles potato chip is a hyperbolic space. It has negative constant curvature. ADS is kind of the space-time analog of a Pringles chip. It has negative curvature, but it's not just a space, it's a space-time, so it has a time direction. And in some convenient parameterization, the geometry is this. If you erase time and put just 2 dimensions, this is a hyperbolic space, sometimes called the Lobachevsky plane, and which is the geometry behind this drawing by Escher. So when you go to z going to, when z goes to 0, you go to the boundary, and the distances are stretched, and you have this. And then Maldacena showed that in the boundary of this of ADS, the conformal, the symmetries of space-time become the symmetries of a conformal, become the conformal symmetries, and so you can place a CFT here. This is one of the great results of string theory. ADS3 you can actually draw. It is hyperbolic space, two-dimensional, the Lobachevsky plane, the Poincare disk, and you evolve it in time. So you can actually draw it like that in 3 dimensions. And it generates, it has a CFT on the boundary. The CFT is two-dimensional because the boundary, if this is 3-dimensional, the boundary is only 2-dimensional. So the CFT has 1 dimension less. And this is 2-dimensional CFT. So it has a Virasoro algebra and the central charge. And the central charge is given by the radius, the curvature radius L of ADS. So a CFT on the boundary of ADS3 has a specific central charge given by that. And we are going to use this formula as well. So now what is the D1, D5 system? And just go back to try to describe things which look like a black hole. Long ago, in the 90s, Strominger, Ashok-Sen, Strominger and Kumrum-Waffe showed, before even Maldacena published the papers in the ADS CFT correspondence, they used a kind of prototypical ADS CFT correspondence to string theory gauge gravity duality to compute the Bekenstein entropy, Hawking-Bekenstein entropy of a system which looks like a black hole and is called the D1, D5 system. This is, well, let me try to explain the ingredients. So first, you take D1 branes, you take a large number of them, and you wrap them around a circle S1. The circle is going to be large. Then you take N5 branes, N5 D5 branes, and you wrap them around a torus, which is made by this large circle S1 and another smaller torus T4. These T4 eventually you compactify, you make it microscopic, but S1 remains large. And then you have a system, a brane system, which can be described in full string theory, and it can be described in the regime where string theory becomes supergravity. In this regime, that string theory becomes supergravity, this is a solution of type 2b supergravity, and it creates a geometry. And the geometry is given by this Pythagoras theorem. It's a 10-dimensional geometry, and you have, well, this is the metric of the sphere, this is the torus, and the important thing are these functions 8.1 and 8.5, which are given like that. They are harmonic functions with a coefficient here which is proportional to the number of branes that you wrapped. And if you look, you can also add, there is a different solution, a more general solution, where you can add momentum along this pink circle, and it gives a slightly different geometry, and I'm going to use this later. But to avoid cluttering the slides, let us deal with the simplest case. So if you look at this equation, this geometry, it looks like a black hole solution. It has the structure of the Schwarzschild solution. Here you have a function, and here you have the same function, and one is the opposite of the other. You're dividing. So this has a black hole structure aside from the other things. But this part here, this radio part, it's not actually radio anymore because you have factors. It creates an event, or it has a structure of that allows us to find an event horizon. If you take limits of this solution, first you can take R going, R is kind of a radial direction because it combines with the sphere like this. If you take R to go to infinity, H1 and H5 both become 1. This vanishes. And you look here, these are trivial, and this is just flat space with some identifications of the circle and the torus, but it's flat space. It has no curvature. So very far from R equal to 0, you are in kind of Minkowski space, with some identifications and with many dimensions. On the other hand, when you take R and go to 0, you can ignore the ones, and these functions, they produce, in these factors here, they produce a deep well, a tunnel, like the tree outside, and it ends in an event horizon at R equal to 0. This particular function, this particular system, the singularity is here at R equal to 0. If you add momentum, you have an event horizon that does not overlap with the singularity, and so you can putting momentum is useful, and I'll do it later. But the thing is, this is the structure. It's easy to see. You go outside this flat space and you go to R to 0, it goes down a well. If you expand this thing for R equal to 0, and you have to make a slight change of coordinates and change R to a coordinate Z, the metric becomes this. This is a near horizon limit for R going to 0. Q1 and Q5 are numbers. They are essentially the number of branes that you wrapped. This factor is the metric of ADS3. The other one is a sphere. This d omega is by definition the metric of a sphere. And finally, here you have a torus. This is the metric of a torus. So in near the horizon, the geometry becomes ADS 3 with a factor of a sphere and a factor of a torus. The presence of ADS 3 tells us that there is a conformal field theory that is equivalent to this ADS 3. And the conformal field theory is a quantum theory. So it has quantum degrees of freedom. And these quantum degrees of freedom are just a different description of the degrees of freedom of that gravitational system. So that event horizon has quantum degrees of freedom given by a CFT. And you can try to count these degrees of freedom and see if they correspond to the expected degrees of freedom of the gravitational solution. The expected degrees of freedom of the gravitational solution are the logarithm, the exponential of the Bekenstein-Hawking entropy, which you can compute geometrically, computing the area of that horizon. What is the CFT that appears in that in that case at the bound at the end of the D1D5 black hole? Well, it is a CFT, so it has a Virasoro algebra with some central charge C. It also has more symmetries. It has some arc current symmetries, which I call J. It is supersymmetric. It has 4, 4 supersymmetries. So it has supersymmetry generators. And they combine into this superconformal algebra, which has a lot of letters, but okay. They actually have an explanation and a correspondence with the geometric picture. So that algebra can be realized by 4 bosons and 4 real fermions. And the central charge you can compute because central charge for one boson is 1, for one fermion is 1/2, and so the total central charge of that theory is 6. But you also have to, the actual holographic description is given by something called an orbifold. You have to take this CFT with that algebra that I showed, and you have to make n copies of it. N is the product of n1 times n5. So it's a large number of copies, and you combine them, identify them under permutations. The copies are all the same, they are identical, and any permutation is good, so you combine them all like that. One copy, which called seed CFT, has central charge 6. If you combine n copies, you have a large central charge 6 times n. So this is the central charge of the actual holographic thing. The stress tensor is going to be a sum of many copies of a stress tensor of a simple superconformal theory. The modes of the stress tensor from the Virasoro algebra, this is in correspondence with this factor ADS3. The other thing here, this part of the algebra, is actually, this part is SU2. And so we have a central extension of SU2. The SU2 comes from the symmetry group of this sphere. You actually have 2 copies of this. You have another set of generators with 2D, one for each SU2 that make the symmetry of S3. And you have a global symmetry corresponding to symmetry group of the torus, which is kind of SO4. You can use this is not an intrinsic symmetry, but you can use it as an organizational principle. And so you have fields with these indices here. You have indices in SU2, and you have indices in doublets of SU2 and SU this factor that appear in the fermionic generator. And I'm ignoring the anti-holomorphic part. There is a different copy which is identical with 2D on everyone. And these are the ingredients of this D1, D5 CFT. The other important ingredient is the orbifold thing. So the orbifold, you can construct an orbifold CFT by introducing a new set of operators called twists, which permute the copies. So you have many copies of the stress tensor. They are all equal, but they are distinguishable, and you can make the permutations like this. You insert a sigma operator or a twist with some permutation. In this case, the permutation 1, 2, 3. When you take the field and go around it, it changes, the copy changes, so the copy 2 becomes copy 3 because this permutation changes 1, 2, 3. Yeah. And well, it's complicated to deal with these. I talked about this yesterday in a group meeting. This orbifold complicates things, so it's complicated to compute correlation functions, etc. Or even if the theory is free, because these introduce non-trivial boundary conditions, and etc. I'm not going to dwell on this today. I'm just marching on. So the CFT, the D1D5 CFT, is dual to a gravitational solution, and it must be a strongly coupled CFT because of the properties of ADS-CFT correspondence. And it's difficult to compute things in strongly coupled CFT field theories. However, there is a space in the moduli space of the CFT, of this strongly coupled CFT, where the fields are free. And then you can try to compute things in this free CFT and argue if they are protected by some supersymmetry theorem that the result is going to be the same in the actual point of moduli space where you have the dual to the gravitational solution. In this free orbifold point, the fields are free bosons and free fermions, and you can organize them with indices like that. You have your 4 bosons, your 4 fermions, and actually you have a lot of them because you can change the copies, but they are all identical. It's convenient to bosonize the fermions in 2 dimensions. 2 dimensions you can do this. You can describe a fermion in terms of a boson, the exponential of a boson. So you can exchange these tube size by bosonic fields phi 2 and phi 1, combining them like that. These make it easier to compute things. And, well, you can build states. There are many states in the CFT. I'm putting here an example of states. These are Raman ground states. They are ground states in the Raman sector, but they are twisted. So you take these bosons here that you bosonize. These are fermions. Actually, they are fermionic modes because you're taking exponentials of phi, but you can write them in terms of bosons, and you act upon this. You act with this upon a twist, and this will produce a field which has some conformal dimension. It has charges under the SU2s that you have in your symmetry, and they have twists. If you take another field and circle RZ, this twist is going to swap the copies of the field you go around. You have a collection of Raman ground states because there are different possibilities because of the different symmetries of the indices that you can put here. And this is an example of a field in the CFT. You can take the field and apply it on a vacuum, and you create a state by the operator state correspondence of 2-dimensional CFTs. Every operator in a CFT in 2 dimensions can be thought of as a state in a Hilbert space. And so you have Raman ground states with twist n, and the actual Raman ground states of the orbifold is a combination of these strands, because this only uses a small number of copies of your orbifold. You have to use all the copies, and so you combine them in things like that. Have states which are given by many permutation cycles. They are complicated objects. And these are the Raman ground states, but there are other states. You have NS chiral primaries, you have excitations of the Raman ground states. You can act upon them with Virasoro modes or with SU2 modes or something. And you have actually an infinite number of states in the theory. These are an example of class of ground states in the Raman sector. Okay, so the black hole is described by ADS-CFT as a CFT, a 2-dimensional CFT with a lot of symmetry properties that come from the other factors of the geometry. This CFT has a Hilbert space. It has a collection of states. And in a way, these states give a description of quantum states that correspond to the black hole. So if the entropy of the black hole should be some kind of, should be counting those states in the Hilbert space. If you take the undefined, the metric that I put before, and you add the momentum that I promised, and you do some transformations and you go to 5 dimensions, you end up with a geometry like this. This also kind of looks like a black hole because you have F and F, but one of, oh, actually no, 8 and 8, 1 over 8, apart from other factors. And 8 has the structure much like the Schwarzschild black hole. So it has an event horizon. This thing has an event horizon at r equal to 0, where 8 vanishes. You can compute the area. It's non-trivial to compute the area because you have to, the string frame, Einstein frame, you have to go from one to the other. But you can do the computation of the area of this surface, r equal to r0. And you find that the area is given by this. This is the number of branes in one brane, d1 branes, d5 branes. And these are the integer number of momentums that you can put going around one direction or the other direction in that donut that I drew. So it gives you a finite area. This is a purely geometric computation. Okay. On the other hand, you have Cardy's formula for the CFT. And you know the CFT now. The CFT has central charge C given by the radius of ADS. I think it wasn't clear in the slides, but the radius of that ADS3 factor that appears in the solution is given by the number of branes. So if this L in that ADS3 that appears in the black hole, you can compute it. And if you insert this here, you find that the central charge of the CFT is this. Well, we actually had written this formula. Okay, so you take the central charge and you put it inside Cardy's formula. The number of states with momentum NL and momentum NR then will be the product of the number of states with momentum NL, momentum NR, if n is very large. And, well, when you replace the central charge, you get this. And if you take the logarithm of these exponentials, you get this here. So when you compare, you have a completely geometric computation that gives you this for the area of that system, that black hole. And you have a CFT computation that gives you this, counting states in the. They are done completely differently, in completely different ways. And they give you the Bekenstein-Hawking formula with the 1/4 and G5, everything, for that system, which kind of, well, we call it a black hole. It is not like the black hole in the center of the galaxy, because it has supersymmetry, has a lot of things, but it is a theoretical solution of a black hole. So string theory, in the sense, is capable of doing some microscopy and extracting the quantum degrees of freedom using this duality, the ADS-CFT duality. And this was one of the great successes of string theory in the 90s. Well, that computing that formula was remarkable, and people kept studying what happens. So I still have I have 10 minutes. How many minutes do I have? Okay. So this is what I was going to talk about, but Dmitry wanted me to talk about the dictionary, the holographic dictionary. And then you can ask the following. Well, I did a computation like that, blah, blah, blah. So you have states in a CFT, and you have geometry of a black hole. So is there a way of knowing whether what a specific state in the CFT, what does it correspond to? Is there a geometry associated? Is this geometry a black hole? The black hole is a superposition of all these states? How does it work? It isn't clear from that picture. So people have been, over the last 10 years, I don't know, studying many ways of constructing supergravity solutions that are not black holes, but and that correspond to specific microstates or specific states in that CFT. By now, there are many different families of solutions called superstrata and 2-charge geometries, 3-charge geometries. There was a fuzzball program by Mathur and people like Joseph Benna, Nicholas Warner, David Turton. People have been working hard to construct these solutions. And there is a dictionary between solutions and states. And I'm going to try to describe very briefly a specific example of a 2-charge geometry, which was found a while ago by people. The dictionary was made a while ago by Marika Taylor, Scandries, and people like that. And I'm just going to sketch how the states correspond to the geometry. So you have, it's kind of involved. You first take a fundamental string in R5. This is a construction by Mathur and also Madsen, Looney, Mathur, Madsen, and Mausch. So you take R5 and you put a string going around. The string can be described by a profile, 5 coordinates, which I call G. And V is a parameter on the loop. You can decompose this loop in Fourier modes. It's just a function and you decompose it in Fourier modes. And you combine the coordinates G1, G2, G3, 4, 5 like that. And you call the Fourier modes by these names. This is just a definition, specific combination of Fourier series. Simple. It's a closed string oscillating. It is given by Fourier series. Many of these A's can be 0, for example. Okay. So you take this thing and you apply STU dualities of string theory. If you apply a U duality, that system goes to the D1, D5 system with a metric in 6 dimensions given by this. It's a collection of functions and forms. Omega is a form, beta is a form or one form, etc. It's a geometry. And it is described by a set of functions. And if you look, you will see that it boils down to functions Z1, Z2, Z4, and these A and B. These are the basic ingredients that you use to construct this geometry. And these functions are given by integrals of G's. The G's that you made your string, the parameterize your string in the other frame. So you have that string given by the G's, you apply a U duality and it becomes this object with the functions given by your string profile as these integrals here. Good. So what is the translation? The translation is that in the CFT, if you take those Raman states that I put before, Raman ground states, and you combine them in a superposition with constants here, this is just a superposition with a few constants, A's, you will produce a state. This is a specific superposition of states. You know who these are, and you put some parameters. You can choose them. You can choose the parameters you want, and you will produce different superpositions. These parameters correspond to the Fourier modes of the string in the original system, like this. This is the translation. So you can either choose a Raman ground state, a superposition of ground states. So you choose these A's. You use this formula to find the little A's, and you use the little A's to draw a string in S5, in R5. And then you take U duality, and the string becomes a black hole, a D1D5 black hole. A simple example is if you take just this combination of Raman fields, it's just one field, but you take it to the power n over n to complete all the copies in the CFT. So it's a twisted field. If you do the dictionary, this will produce something called a round supertube. The blue string that I drew here in R5, it's just a round circle with some radius a, little a. And that thing becomes, you apply U duality, that thing becomes a d-dimensional black hole, which is this thing here. It's just, it has a structure of kind of a black hole, Z1, Z2, Z1, Z2. And Z's are given by these complicated functions, but whatever. And if you analyze this geometry, so you take limits of these functions, r goes to one side and goes to infinity or go to 0, you see that when r goes to infinity, it's just flat space with some identifications, and it's written strangely here in some spheroidal coordinates or something, but it's just flat space for r very large. But when r decreases, it makes a tunnel like the D1D5 system, but the tunnel doesn't have an event horizon and it doesn't have a singularity. It ends up in something like this. So it ends in a smooth geometry characterized by this little number a. When a goes to 0, if you take this and put a equal to 0, this complicated thing becomes our D1D5 system, geometry that I had before, which has a horizon. So this is a smooth, horizonless, non-singular geometry that looks like the D1D5 black hole, but it's not a black hole. It has the same charges as the black hole. The geometry is similar, but it doesn't have a singularity or a horizon. So many geometries of these kinds that do not have singularities, but look like black holes outside in the region around the horizon, or what would be the horizon, have been constructed by this group of people. I don't work with this. I don't know much, but I know that many have been constructed, and they correspond to specific states in the CFT. You can, and so this is one example of the dictionary, a precise example of the dictionary. And now it's over. Okay. So this is it. If anyone has questions, I passed 1 minute.
Okay, thanks, André. Let's open for questions.
I can start with a question. So first of all, you said that these solutions resemble the black hole. So in which sense do they resemble black hole?
Well, it resembles this last one. If you take limits, it is going to, if you analyze the geometry, it's going to look precisely like the one of the black hole, up to a region at the deep end of the well, which is of order of this parameter array. So you have this have these theorems in general relativity that a black hole has no hair. So you have it is described. Classical black hole is described by three numbers: the charge, the area, and the charge, the mass, and the angular momentum. So it's just three numbers, which is actually what I said. These three numbers can't account for the microstates. And the problem is that the horizon of the black hole is a null surface, and any matter that you try to put around it falls down very fast. So you can't keep a structure around the horizon. You can't make something that would be like a black hole, but is supported. You can feel the black hole with mass up to the horizon, and then it ceases to be a black hole. And this is what people thought. And these solutions, they are constructions that change the geometry just around the horizon, so they kind of escape the no-hair theorems by constructing something that has the same charges. It has the same angular momentum. It's difficult to extract this information from just the geometry. You have to compute the angular momentum, the mass, etc. And it has the same degrees of freedom, the same parameters of the black hole. And the geometry looks like the same up until the near the horizon. As far as I understand, they build these things by putting magnetic fluxes, which I didn't write here, which end up in a way supporting the geometry in some sense. But I don't know much. So yeah, they resemble the black hole. The geometry looks like up to a region of size A. If A is small, it's going to look like the black hole a lot, up to a very small region.
Okay, so the next question, I think you mentioned that actually these states are not enough to account for the entropy.
Oh yeah.
And, but on the other hand, I think you construct them directly from the CFT states. In the CFT states, you have enough states. So I'm not sure. There seem to be two conflicting statements.
This is one question that these microstate geometry people keep trying to answer, because yes, you don't have. They found a large class of different classes actually of solutions, which they are a large class of solutions, but they are not large enough. So if you count the number of solutions that have these properties, they are parametrically smaller than the number needed for the entropy of the black hole. And so what are these states that are not being counted? I don't know.
Well, this from the CFT side, because you have a map. You explained there's a map from CFT to the solutions.
Yeah, but
somehow used only I don't know, this basic twist states or whatever.
The Bekenstein-Hawking computation, it uses the Cardi formula. So you have a limit and you kind of only know the center of charge. It is very coarse-grained in the sense that you don't know which states are doing what. You have a lot of states, they are producing a black hole, but you don't know which ones do what. These dictionaries, on the other hand, they give you a geometry for a state, but there are many more states and there are many more supposedly geometries. I don't know, and they keep trying to construct more geometries which would account for the other missing states. But this is a problem. These geometries do not fill the number of states necessary for the Bekenstein entropy. You can assume that they are part of the states, and there are many others that will also contribute.
More questions? Okay, I do have one.
Mm.
So when you were showing the the line element for the D1, D5 system, at some point you reduce it to 5 dimensions.
Here is always 10-dimensional, but in the end I cheated.
Yeah, can you elaborate a little bit on that? How do you do it?
So this is 5 dimensions. This is cheating because you actually, to find this, you need to find to start with something different than the one I wrote. This one doesn't have momentum. It only has N1 and N5 branes. And the other one had two new numbers, NL and NRR, which are momentum going around this pink circle. But you can do the compactification in this way. This has 10 dimensions. 4 of them are compact. This T4 you will shrink down. So you just do compactifications of this dimension, Kaluza-Klein compactification, and you remain with 6. I don't remember where the other one goes. This this Y is a large circle. You don't compactify this, but you compactify these 4. I don't remember where the other direction went. I don't know. I can find out.
No worries. Okay, more questions? If not, let's thank Andrea again.
Thank you very much.